So when we're talking about acid and base equilibrium, we have to know whether we're dealing with a strong acid or a weak acid. Okay, because that will tell me whether or not I have an equilibrium system set up or not. Okay. So a strong acid, and here are your 6 strong acids, are considered strong because they ionize completely. I get all the H's removed from the molecule. So whenever I have a strong acid, I do not have equilibrium, I just have a left to right reaction. So this reaction, although I can write it as equilibrium, is really, because HCl is strong, this is really just a left to right reaction. So whenever I have a strong acid, I only have a left to right reaction and not an equilibrium situation. Okay, and you have a table of acids. Table 15.1 in your book has a table of acids, strong and weak, listed in order of strength. And the strong acids are all above hydronium. Hydronium, remember, is also acidic. Okay. So that means that the other acids are weak acids. So when we look at whether or not an acid is strong or weak, we're really looking at how easily does it give up the H+. These 3 give up H+ pretty easily, so they're considered strong. HF, because that fluorine is so electronegative, it does not readily give up the H+, so it is considered weak. Likewise with these guys, none of these guys really want to give up that H+ very much, so they are all considered weak acids. So the more electronegative something is, the stronger the acid, if you're looking at a binary acid, and also if you're looking at size, atomic radius. If you remember from last year, atomic radius increases as you go down a group. So the bigger the radius, the easier it is to take the H off. Okay, we also have something called oxo acids, which are simply acids that have oxygen in them. So typically acids form from polyatomic ions. So the more oxygens you put on an acid, an oxo acid, the stronger the acid is. And that's because, remember, oxygen, hydrogen form a very polar bond. Oxygen is the negative end, hydrogen is the positive end. So the more oxygens I put on, the stronger the pull of that one electron away from the hydrogen. So you can see down here, HClO4, perchloric acid, that's considered a strong acid. That is the strongest of those 4 because it has the most oxygens on it. Okay. So when we're looking at conjugate pairs, the stronger the acid, the more likely it is to donate an H+. So the stronger an acid is, the weaker its conjugate base. And we're going to look at this mathematically here coming up shortly. So the stronger an acid, the weaker its conjugate base, and likewise with the base. The stronger the base, the weaker the acid. So when we're looking at which direction will something go, we look at which acid is stronger and which base is stronger. And so since a stronger acid is more likely to donate an H+, and the stronger base is more likely to accept an H+, when we look at a reaction, we go from strong to weak. So here's table 15.1, relative strength of acid base. And if you look, these are your strong acids right here. Okay. Now one thing I want to point out is that remember when we look at Bronsted-Lord, we're looking at the transfer of a single electron. So since sulfuric acid has 2 hydrogens, the first hydrogen comes off completely and gives me HSO4. So when I'm looking at this reaction, this is left to right. I get HSO4 minus plus H3O plus. That's one step. The second hydrogen is going to come off in the second step. So that's going to be HSO4 minus plus water. Since HSO4 is a weak acid, that's going to be equilibrium. And we're going to look at these types of acids, which are called polyprotic acids because they have more than one H+. We're going to look at those in a little bit. So, now we're to the equilibrium part. We write equilibrium expressions only for weak acids and weak bases. So here's a typical weak acid, acetic. Here's a typical weak base, ammonia. So we can write a K expression for this equilibrium situation. We can write a K expression for this equilibrium situation. So if I'm writing the equilibrium expression for an acid, it's a Ka for acid. If I'm writing the equilibrium expression for a base, it's a Kb for a base. And you'll notice water is not included in the equilibrium expression because it is a liquid. So, coming back to this idea of the direction of equilibrium, which direction is this favored? Is this going to be product favored or reactant favored? So I look at my two acids. HBr is a strong acid. Acetic acid is a weak acid. So based on the acid strength, I would predict that the reaction would tend to go in this direction with only a little bit coming back this way. Likewise, acetate is a stronger base than bromide ions. So again, I would predict that the equilibrium would lie to the reactant side, that if I mixed these two things together, they would pretty much stay like that. If I mix HBr and acetate, it's going to pretty much go from that direction to that direction.